Hi guys, this is Vicky, and today we're going to talk about how to calculate pHs in a buffer solution. So I'm going to try to summarize this in a very simple way. And if you guys remember, what are buffers? So buffers are a solution, right, that acts as a sponge to absorb extra H pluses and OH minuses to prevent drastic pH changes, right? Prevent drastic pH changes. Okay, so this just means that buffers are going to be consuming up its extra protons and hydroxides to just kind of make sure that the pH doesn't change in that particular solution. Now, buffers are composed of either a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay, so let's just look really quickly. So for instance, if I have a titrant here and a beaker, and let's just assume that I have a weak acid, HF, okay? And we know that weak acids, by definition, they do not like to dissociate, okay? Now, it also has its conjugate base, okay? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so let's just assume that in this particular container, I have a buffer. Okay, now it just so happens that I'm going to start adding a strong base, for instance. Now, if I start adding a strong base, the strong base is going to start to, okay, pair up with the OH minuses. Do you see that? So, in this scenario, I started out with 7 moles of HF, right? And I started out with 1, 2, 3, 4, 5, 6, 7 moles of F minus. Okay, so I started out with 7 moles of HF and 7 moles of F minus. And I happen to have added, okay, I added to this particular buffer, I added 3 moles of OH minus. Now, all 3 OH minuses are going to be paired up with H's from hydrofluoric acid, leaving the F minuses to float around. Now, if you look at this, okay, has there been any change in free floating H pluses? Any new free floating H pluses? The answer is no, right? And because the answer is no, you can say that pH has not changed, because what is pH? It's negative log of concentration of H plus, right? And if by definition I don't have any changes in H pluses, I will have no change in H plus concentration in my negative log equation, and hence I will not have a pH change. Does that make sense? So basically, what we are going to do now is we are going to be looking at how do we then calculate Ka values and pH values when we have a buffer system. So for instance, okay, I have HF and I start out with HF, and it just so happens that I'm going to add NaOH. We know for a fact that NaOH is a very strong base. So the strong base will dissociate 100%, which will be driving the whole equation to the right. This means that I am not only going to be creating water, but I'm also going to be creating salt. Now, by definition, we know that Na is a very soluble ion, and therefore I am going to just kind of eliminate the Na, okay, making the OH minus an ion. So essentially, my real equation is going to look like this: OH minus H2O plus F minus. If they tell you that they have, let's just say you started out with 2 molarities and 1 liter of HF, and you just so happen to add 0.5 molarity of NaOH, and let's just say that's also like 1 liter. Okay? So first thing first, what I need to do is I need to create an ice table and I need to figure out how many HFs I'm going to have remaining. So this is my first step. So step 1 is to calculate how many OH minuses I will have, how many HFs and conjugate bases I will have left over once all of the strong base have been used up. So that means I have to switch everything into moles. So I'm going to go back here and I know that M times V equals moles. So 2 times 1 equals 2 moles of HF. And I know 0.5 times 1 would be 0.5 moles of OH minus. So again, I know that I have 2 moles of HF and I have 0.5 moles of OH minus. I don't have any water or any conjugate bases that has been started in the beginning, right? And I know that the limiting reagent is OH minus because this is the strong one and it's going to be driving the whole reaction to the right. So that means I am going to be using up 0.5 moles of HF, adding 0.5 moles of H2O, and adding 0.5 moles to F minus. That means I end up with 1.5 moles of HF, 0 moles of OH minuses, 0.5 moles of H2O, and 0.5 moles of F minus. But again, we know that this water, because it's pure liquid, it will not partake in the equilibrium equation, right? So all I need to do now is I just need to focus on the amount of HF and F minuses that remain in this particular solution. So what is my step 2? My step 2 now is I need to figure out, okay, how much HF naturally dissociates in a solution once all of the OH minuses have been matched up and we got rid of them, right? And have been consumed by the buffer system. So in step 2, what I do is I am going to use HF, and I know this is going to ionize into H plus and F minus, and they have to give you a Ka value. And I'm just going to make this up, and let's just say 10 times 10 to the negative 2. And so what I'm going to do now is I am going to create molarities from these numbers. So we know that we added the 2 volumes up here, 1 liter of HF and 1 liter of OH minus. So that means I have 2 liters in total. Okay, so I'm going to divide these by 2 liters and I end up with, what is 1.5 divided by 2? I end up with 0.75 molarity, right? 0.75 molarity. So that is my new concentration after the buffer system has completely consumed up all of the OH minuses. So if I were to just draw this out for you, okay, it just means that I have HFs, okay, and I have HFs. Okay, I have HFs, and I know that HF naturally also likes to dissociate. It's just so minute that we just say that less than 5%. We just don't know how much it actually dissociates. Okay, and then we added OH minuses, but we also added a fraction of OH minuses than what we had, right? So let's just say we had four HFs, and that means I only literally added one OH minus. So this OH minus is going to be paired up like so. And whatever HFs are remaining in the solution, they also naturally will dissociate. Okay, so step 1 was up to here, and starting step 2 is I need to figure out, based on the remaining HFs, how many these are going to dissociate based on the Ka value. So I'm going to draw out my ice table one more time. So here's my ice table. And I'm starting out with 0.75 molarity of HF, 0 molarity of HF because I don't know, but I'm going to start with 0.75 molarity of F minuses because if you look, this is the F minus that remained, right? That got produced due to the OH minus. So from here, I am going to subtract an X amount, add an X amount, add an X amount, and just do regular ice table. Okay, 0.75 x 0.75. And then what is my step 3? My step 3 is basically going to be using Ka to figure out my x value, right? And Ka expression is always products over reactants, so H plus over F minus over HF, and that means it's 0.75 times x over 0.75 is equal to 4 times 10 to the negative 2, okay? And I know that my x is equal to H plus concentration, which is 4 times 10 to the negative 2. Now, what is my step 3? My step 4. Step 4 is basically doing the calculations for the pHs. So what is pH? It's negative log of concentration of H plus, and I just so happen that I have the H plus concentration, and based on that, I end up with, because I'm going to be plugging in that number right there, I end up with negative log of 4 times 10 to the negative 2, and I end up with 1.39, and that is going to be my new pH once all of the OH minuses have been consumed in the buffer system. I hope this makes sense, and if you guys like it, please give it a thumbs up, and don't forget to subscribe. I'll see you guys next time. Bye!